From the Buma succession, it suggests that the outcrop section represents distal part of turbidity deposit. Besides that, Ophiomorpha recta is associated with quite oxygenated environment, especially that is episodically interrupted by turbidity flows, typically in bathyal and episode environment. Ophiomorpha annulata was observed well preserved in the sandstone bed, which suggests deposition within the lower bathyal to upper slope. Furthermore, the Ophiomorpha rudis is associated with high energy proximal and axial turbidite deposits. Stop 2 is located in the central part of Clias Peninsula, which consists of steeply dipping sand shale succession of deep water temburong formation. The outcrop is represented by more dominant sand beds of TA compared to the preceding Stop 1. Dominant TA compared to TE probably represent the position of proximal turbidite environment, followed by a shorter interval of mud suspension deposits. Ophiomorpha annulata occurs quite abundantly at this outcrop, which is associated with deposition in the lower bathyal to the upper slope environment. Stop 3 represents basal belite formation deposited unconformably overlying deep water temburong formation. These formations are separated by regional unconformity known as the DRU. Basal belite formation is composed of predominantly conglomerate with a few interbedded coarse-grained sand deposited in fluvial environment. The conglomerates are composed of various grain size ranging from boulder to pebbles, which implies deposition in the high energy condition. The upper part of belite formation, whereas it consists of finding outward sandstone and shale succession, a fault was observed 2 meter displacement, which then infilled by shale in the later stage of deposition. Cross beddings were also observed within the sandstone, and burrows belong to Ophiomorpha nodosa was present, which could associated with the deposition in the marginal marine environments. Stop 4 represents West Crocker Formation. It consists of predominant thick beds of coarse-grained turbidite sandstone. The outcrop shows a section that it has undergone intense tectonic deformation, resulting overturned bedding and folding. The presence of footcasts at the base of the sandstone beds implies the bed has been tilted more than 90 degrees, indicating a younging towards the southeast direction. Ophiomorpha nodosa, which was associated with shallow marine setting, was also counted quite sparsely within the sandstone bed, suggesting intermittent shallow marine sediments transportation into the deep water setting. Stop 5 represents the Sequati member of Kudat Slum Formation, which occurs mainly within the central part of the Kudat Peninsula. Overall, this outcrop is dominated by highly steeping beds. It consists of deep water turbidite deposits with predominantly TA, TC, TD, and TE in the lower stratigraphic interval, and TA, TD, and TE in the upper section. Other than that, recumbent fur was also observed at the eastern side of the outcrop, which interpreted as a slum associated with thin sedimentary soft deformation. Stop 6 also represents Sequati member of the Kudat Slum Formation, which predominantly sandstone interbedded with shale. The Buma sequence observed at this outcrop is consistent with that in the Stop 5, which composed of TA, TC, TD, and TE at the lower stratigraphic interval, and TA, TD, and TE at the upper stratigraphic interval. Channel belts were observed consisting TC sandstone with common flame structure at the pinch-out section of the channel. It shows that the section is younging toward the southwest direction. And lastly, Stop 7 is located at the northernmost tip of the northwest Borneo within the northern Sabah terrain. It is dominated by the Kudat anticline and semi-concentric pattern of the rich valley morphology. The sedimentary section is represented by predominantly thick TA sandstone, overlain by TB and TC sandstone, and then capped by thin PE shale. Ophiomorpha nodosa was also observed within the sandstone bed with low abundance and smaller size. This stress fossil is associated with high energy environment, possibly within the proximal part of the turbidite succession. So there are 5 key discussion points identified from the study. However, we will discuss 2 of these points. Firstly, on the West Crocker Formation, it shows succession of thick bed coarse-grained sandstone turbidite deposit as shown by TA, followed by thinner TB, TD, and TE. This observation indicates deposition took place under influence of high energy regime. Alternatively, it may suggest also deposition close to the sediment source area. In the West Crocker Formation, it has been intensively deformed, resulting in structural folding and overturned beds. This event is closely associated with compressional deformation in relation to subduction of dangerous ground towards the Borneo in the early Miocene. Another key discussion that we can touch here is the paleo environment of the northern Sabah terrain. The northern Sabah terrain exposed stop 7 crop consisting of succession of thick TA sandstone beds, thin TC sandstone, and also TE shale. The observation suggests the turbidite event took place within the high energy deposition, which followed by decreasing energy as shown by TA-TC succession and ended by TE, bed mud suspension. It reflects the change of depositional regime from high to low energy, and this observation was also supported by presence of Ophiomorpha nodosa within the sandstone bed in low abundance and smaller size. These stress forces strengthen the fact that the outcrop is deposited within a high energy environment, possibly within the proximal part of the turbidite succession. So to conclude our presentation, my presentation, sedimentary feature provide an indicative signature of stratigraphic position at the beddings, as well as the positional process involved at the outcrop. Stress forces also provide proxy for the position environment interpretation based on their burrowing behavior. Overall, the outcrop observation during the field trip allowed further sedimentological insights to be made and subsequently improve the sedimentological environment interpretation. So that's all from me. Thank you. Assalamualaikum warahmatullahi wabarakatuh, and hello everyone.
Okay. Oh, clear network dulu. Okay. Bismillahirrahmanirrahim. Good evening lah kan sekarang ni. Okay, Amin dah boleh ke? Hello Amin, ya. Yeah. Boleh. Okay, start. Number 2. Together with me today, I have Sir Muhammad Nur Amin, who will be assisting me to ensure that the sessions run smoothly. We will begin the session shortly. I would like to request everyone to please put your microphones on silent mode. If you wish to ask any questions, please use the live Q&A chat box. Thank you very much for your kind cooperation. We will now have the privilege of listening to the first presenter of the sessions from Mr. Paul Kia Jun from Basic Front Labs Asia, Malaysia.
So good day to everyone here. My name is Kiajun and today I'll be presenting the details of my previous final year projects entitled Pore Pressure Predictions using the 2D Basin Modeling software. So this project was carried out in the collaborations with the Basic Lab Asia company BFA. So with help from both of my university supervisor, Madam Shazwani, and BFA supervisor, Mr. Eduardo. So I managed to reach the objective of this project with a success. Before we continue further, this is the outline for today's presentation, where the flow will start on with a short introduction, literature review, methodology, results and discussion, and on with the conclusion and recommendation. So in simplifying my final year project for your understanding, my projects revolve around pore pressure prediction using 2D basic modeling technique. In this project, the software used is TemiFlow, which is the BFA corporate exclusive basin modeling software. So at the end of the simulation, the evaluation are done on the overpressure model generated. As you can see, this is some background study that I have carried out on the overpressure mechanism. So there are various mechanisms that contribute to the development of overpressure, which can be summarized into 3 categories. Next, these are the problem statement in my project, which including the main study of it, which is questioning the ability of TemiFlow to reconstruct the evolution process of Pelota Basin, which is our study area, and predict the pore pressures in the region. Thus, my objective for this project are very simple. The project aims to build a pore pressure model using the basin modeling technique. And from the result, we can also identify the factors that contribute to the development of overpressure in the regime, and finally, to evaluate the pressure distribution in the study area. So, as shown in the slides, these are some of the literature review that I have carried out on the study area before engaged in the project. And from these articles, I managed to understand the various overpressure mechanism and the application of Bayesian modeling in pore pressure prediction. Alright, moving past that, let us talk about my project methodology. My project workflow can be summarized into 5 main steps, including review and understand the purpose of each of the input data provided, setting up the initial simulation model, after that, moving on to the generation of overpressure model using the Bayesian modeling software, and from the result, I will identify the main overpressure factor or mechanism in the basin. And last but not least is the evaluation of pore pressure model. This slide shows the procedure to set up the initial model for pore pressure simulation. Next, this is my initial model of the Pelotas Basin to carry out my pressure simulation. Based on the literature review, there are few potential source rocks in the basin, which are the organic shale containing the type 1 kerogen and organic shale marl containing the type 2 kerogen. So moving forward, I will talk about my result findings. The figure shown represents the initial pore pressure in the basin predicted using the Temeslow software without the petroleum generation scenario. And this is the overpressure model obtained. Technically, overpressure can be calculated via the difference of pore pressure and hydrostatic pressure. In this model, the maximum overpressure recorded is 27.98 megapascal. To validate the accuracy of the model pore pressure, calibration is done on the provided well data and the simulation data. However, due to the absence of pressure data in the given well, calibration is done based on the temperature data. This is because the temperature at present and during the basin evolution is one of the parameters to pressure calculations in the model. Thus, they still can be used as a calibration. So as observed, the line in both calibration of VR and temperature represent the simulated values. Meanwhile, the mini points indicate the observed data on the tracks. So if you can see, the resulted simulation values can be said is quite close with the well-logged data, implying our model in this project is quite reliable. This slide shows the pressure profile at one of the locations highlighted in the Pelotas Basin. So you can see that the overpressure start to develop at the change of the lithology formation from the organic shale marl to shale, which has a lower permeability. So if you can see, the rate of the increase of pore pressure started to decrease when it's entering the conglomerate formation. So this profile is also correlated with the mud weight profile generated by the software. The purpose of the mud weight model is to provide us the information if drilling were to conduct in this section of the basin. So during drilling, the main objective is to keep the mud weight properly above the pore pressure to counter the overpressure regime. Next, I'm going to show you the overpressure evolution in the Pelotas Basin over the time generated by the software. Based on the literature review that has been done, there are possibility of hydrocarbon existing in the basin based on the seismic survey that have been carried out recently. However, due to the location of the basin situated in the ultra-deep water, there's no exploration activity has been carried out up until today. In conjunction with that, I have generated a petroleum generation and migration simulation using the software. This slide shows the result and where is the hydrocarbon accumulation in the basin. So in parallel with that, a new overpressure model is also generated with a maximum overpressure value recorded, which is 31.84 megapascal. So the comparison shown in this slide is the comparison between the initial model and the updated one. So to ease our interpretation, the same scale is adjusted and applied into both of the models. And clearly, there is an obvious difference between the two overpressure models. So based on the graph, it can be seen that both the initial and updated model display a clear distinct value of overpressure starting at the depth of 5,000 meters up until the end. So this variation of both of the models are further evaluated in the next slides. So this is the comparison of the initial model of overpressure evolution on the left hand side and the updated one on the right hand side. So in this comparison, it can be seen that these two evolution scenarios begin to vary at the time of 40 million years ago. As mentioned in the journal articles, the generation of the hydrocarbon might introduce the occurrence of abnormal pressure in the subsurface. In conjunction with that, it can be inferred that the generation of hydrocarbon could be initiated during this particular timing of 40 million years. So in this slide, it is evident that the hydrocarbon generation starts at around the time of 40 million years ago, which is Eocene. So it is
All right, thank you for the presentations. Now, okay.
Hi, good afternoon, everyone. Is there any question from the floor?
Thank you very much to
You also stop.
40 million years. So in this slide, it is evident that the hydrocarbon generation starts at around the time of 40 million years ago, which is Eocene. So it is no doubt that the generation of the new fluid, which referring to the hydrocarbon into the formation, was contribute to the development of overpressure. So in conjunction with that, thus the portion of the top three layer lithology is replaced with the shield. So if you can see from the result, there's an apparent pressure variation can be observed at the top of a formation where the shield is introduced into the formation. So again, a pressure profile is obtained at the same location for the analysis purpose. So if you can see, the initial pressure profile shows there is no overpressure developed in the organic shield mound. However, in the updated model of the scenario tested out, there is already a small magnitude of overpressure that has been developed upon the topmost formation of shield facies. Therefore, both of the testing prove that the low permeability of lithology shall contribute to the development of overpressure in the subsurface due to the compaction disequilibrium regardless at any depth. This slide shows an example of tight window of a mud wave. So the evaluation is done on the overpressure model with the hydrocarbon generation scenario along with the mud wave profile and fracture gradient profile. So during drilling, if you use a mud wave with a density that greater than the defined value, your well will be overbalanced and you are able to counter the overpressure regime. However, it is important to know that if you use a mud wave that is too high, which exceeds the geostatic stresses or the fracture gradient, you have the risk to fracture the formation. In contrast, using a mud wave density less than that, your well will be underbalanced and there's a risk of kick and blowout to happen. So in conjunction with that, the ultimate precaution that needs to be conscious is that to maintain the mud wave to stay between the mud wave gradient curve and the fracture gradient. So spraying too close to the fracture gradient will induce fractures in the formation and create unnecessary mud losses. But however, spraying too close to the pore pressure gradient will cause the well bore instability and increase the likelihood of the well bore influx to occur, which is the blowout. So in conclusion, the basic modeling technique is able to predict a pore pressure model. The software enables the user to predict and simulate various scenario testing. So from our project, we can identify that a low permeability of lithology shall start contributing to the development of overpressure in the subsurface, regardless of any depth, according to the compaction disequilibrium theory. So hereby attached are some part of my reference. And thank you for your listening.
Thank you very much, Mr. Paul Kiajun, for these excellent presentations. So we now look to invite questions from the members of the audience. Dear delegates, please use the live Q&A session chat box to write your questions.
Thank you, Madam Shas. So, good afternoon, everyone. So, I would like to open the floor for Q&A sessions.
All right, from the live Q&A session, there's no yet any questions from the floor. So I would like to ask you, Mr. Pokajun, on your findings. Right, based on your studies, right, you are predicting the pore pressure using the 2D basin modeling technique. All right, so is there any other techniques that you use, okay, to compare with the predictions of the pore pressure in the studied basin?
Okay. Well, because I don't when I was carrying out a project, so I didn't receive any um like the real life data of a pressure from the Pelotas Basin. So technically, the only input that I have was the temperature data. So I did a calibration of the accuracy to check whether the model software is it performing good in simulating a real life case in the Pelotas Basin, and I can see that from the results, it's quite close to the provided temperature data. So I would say the software is actually performing quite good, and yep, yeah.
Thank you very much, Mr. Paul Kiajun, for these excellent presentations. We are now would like to move to the next presenter of the sessions. Please welcome Mr. Muhammad Zul Hakim from Basic Frame Lab Asia on the title of Petroleum System Modeling on Pelotas Basin, Offshore Brazil using 2D Basin Modeling Approach. Please join me in welcoming Mr. Muhammad Zul Hakim to the podium.
Right. If the petrol system is working, how well it is, how much volume it can produce, what is the remaining potential, and is it economically viable? If the petrol system is not working, why it is not working? Is it because the process or because of the elements? Moving to basin modeling simulates the geological, physical, and geochemical phenomena driving a basin evolution, such as deposition and compaction, period and term history, generation of hydrocarbon, expulsion from the source rock, and also the migration of hydrocarbons. It defines the formation and evolution of a basin through geological time, and it helps determine the presence and the quality of the petroleum system components, as well as the timing of the operation of the different processes which leads to the formation of hydrocarbon accumulations, which associated with the uncertainty. The Delta Basin is an untapped hydrocarbon province comprising around 280,000 kilometers square basin margin located on the southeast coast of Brazil, bordering the Uruguay to the south. It has around 7,000 meter thickness of Cretaceous and Tertiary fossils that have been deposited in the basin, including both Paleocene and Albensource rocks. The objective of this study is to establish the hydrocarbon prospectivity of the Peltas basins, including Paleocene and Albensource rock, through the basin modeling approach. Brazilian margin consists of complex morphology such as volcanism, structural height, and salt diaparism. However, in the Peltas basin, there is no salt that has been identified in the basin. Based on the seismic section and also the sequence stratigraphy, we can see that the Peltas basin only associated with simple propagation and retrogradation sequence. The Peltas basin evolved as a result from the continental fragmentation of the Pangaea during the early Jurassic, leading to the South Atlantic Ocean formations. From the image below, we can see that the two continental plate with the South American plate and the African plate started to break away during the early Jurassic. That leads to the formation of South Atlantic Ocean formation during the Campanian age. An early Barremian basalt flow fills the basin base. These basalt levels are followed by tuff, conglomerate, and continental sandstones. A first appearance of shallow oceanic facies occurs during the Albian and Cenomanian. During Santonian and Campanian, a continental deposit occurs and leads to an upward increase of shell proportions. Finally, oceanic facies reappears during the Paleocenes. From the lithology description, a Barremian basalt flows fills the basin up to this area, followed by the Albanian and Cenomanian oceanic facies deposits. During Santonian and Campanian, a continental deposit occurs and leads to an increase of shell proportion up to late Cretaceous. Finally, oceanic facies reappears during Paleocene and fills up the basin up to today. Now we are coming to the workflow for our 2D basin modeling, where we are going to start first with data collecting and analysis, then moving to the model building, where we are going to create our present day geometry, and then after we finish with our model building, we are going to assign our model with the faces and identification of the source rock. And after we finish with that, we are going for the boundary condition, where we are going to insert the input for temperature and also the heat flow. For the simulation process, we are going to launch two simulation process, which is the first one is the pressure temperature simulations, and the second one is the full density migration simulations. And after that, we are going for a visualization and post processing. During model building, a total of 14 stratigraphy layers has been identified in the Peltas Basin from Berryman to Holocene age. A lateral variation of facies can induce potential stratigraphic traps. A good sand proportion deposit has been identified at the slope base, and it is equivalent to the proven African turbidite target. A cluster model is also being included in the model building, consists of mantle, upper crust, and lower crust, which allows for a better thermal definition within the model. And this is the result for our model building, where we have managed to identify the stratigraphic unit and also include the cluster model for a better thermal definitions. During source rock definitions, we have identified two potential source rocks. The first one is the organic shell, and the second one is the organic shell mold. For organic shell, it has a TOC value of 50% and a hydrocarbon index of 464 mg per gram. It is considered as a type 1 kerogen. For second source rock, it has a TOC value of 2% for Messinian and Sierra H, and TOC value of 50% for Turonian H, and it has a hydrocarbon index value for 462 milligram per gram, and it is considered as a type 2 kerogens. This is the result from our simulation process, where we are going to calibrate our temperature model and maturity model with our actual data. From this log, we can see that our temperature and maturity model is well calibrated with the actual data. Bear in mind, if our temperature model is not well calibrated with the actual data, we may need to make changes in the boundary condition as well as the maturity data. If the model is not well calibrated with the actual data, we may need to make changes in the lithology setting. For visualization process, we take the hydrocarbon liquid saturation model to delineate the hydrocarbon accumulation. And from this model, several hydrocarbon accumulation have been identified from early Oligocene and early Miocene sandstones, marked by A, B, and C plot. For A plot, it is identified as early Oligocene turbidite sandstone that has a total mean mass around 12% of gas, and the rest is hydrocarbon liquid. For B, it is identified as early Miocene turbidite sandstone that has a total mean mass of hydrocarbon gas around 40%, and the rest is hydrocarbon liquid. For B, it has around 50% of hydrocarbon gas, and the rest is hydrocarbon liquid. In this hydrocarbon accumulation saturation model, we can generate a hydrocarbon accumulation evolution through time, where in this video we can see where the hydrocarbon started to migrate and also it accumulate to the potential reservoir. In conclusion, the main source rocks within the study area are organic shells and organic shell mounds. There is two main plate types that have been identified from the Peltas basins, which is the first one is the turbidite sandstones during early Oligocene and early Miocenes, and the second one is the upper slope sandstones during the early Miocenes. The reservoir is filled up by liquid hydrocarbon, where it has more than 60% of composition made up of C6 components. And to conclude this presentation, 2D basic model allows us to predict and understand on hydrocarbon generation and migrations. Hence, it improves the prospectivity within the study area. Thank you.
All right, thank you very much to Mr. Muhammad Zul Hakim on the great presentations. So ladies and gentlemen, as we have moved on to the next presenter soon, I'm afraid that we can entertain only one question from the floor. So without further ado, dear delegates, please raise any questions in the live Q&A sessions chat box if you have any questions to the speaker. Okay, from the live Q&A sessions, I don't see any questions yet. So let me have my questions to you, Mr. Zul Hakim. So from the title, you are studying about the petroleum system modeling at the Paleotas Basin. So throughout the research, did you find any limitations or any parameters that you couldn't solve from the available data?
All right. During my project for 2D basic modeling, I have received temperature and also the vitrinite reflectance data from the fields. I believe that the data uh, is good enough, and also is for 2D basic modeling, it is more than enough to evaluate for hydrocarbon migration and also for accumulations. Because in 2D migration, 2D basic modeling, we only want to see whether the basin have the potential for hydrocarbon accumulation and also the migration. Thank you.
All right, now we move to the next presenter of the sessions. Please welcome Mr. Muhammad. Please welcome Mr. Mukris Mubin from BASIP Front Lab Asia. He will be presenting on the insight on deep water turbidite sedimentary features from outcore Icer Ps at onshore northwest Sabah, Malaysia. Please join me to welcome Mr. Mukris Mubin at the podium.
Assalamualaikum warahmatullahi wabarakatuh, and hello everyone. My name is Mukris Mubin and I am representative from Basic Front Lab Asia. Today I will present on the insights on deep water turbidite sedimentary features from outcrops in onshore northwest Sabah, Malaysia. So without further ado, the outline for my presentation will comprise on introduction and brief discussion on the geological settings, as well as we go through the observation from the 7 stock outcrops, and then we will discuss on few key discussions from the observation, and lastly we will go through the conclusion. The water turbidite system have aroused great interest among the scientific community, largely because of its economic hydrocarbon reservoir potential, including that discovered in the deep water of northwest offshore Borneo. For the subsurface evaluation, seismic data alone is often insufficient to understand the detail of reservoir insights. Therefore, outcrop study is required, especially to understand the sedimentological properties and reservoir architecture elements. This study discussed findings from the turbidite sedimentary features based on outcrop observation in the northwest Sabah. It comprises of deep water turbidite outcrops from 7 locations in the Klias and Kudat Peninsula and Kota Kinabalu, Sabah, Malaysia. So Klias Peninsula is underlain by Paleogene-Neogene sedimentary rock, namely the Crocker, Temburung, Setap Shale and Belite Formation. The Crocker Formation is composed of predominantly shelly turbidite sediment deposited during the late Eocene to early Miocene. Meanwhile, the Temburung Formation comprises mainly argillaceous rock of turbidite sequence characterized by rhythmic repetition of siltstone and shale. The Setap Shale Formation is composed of thick dark grey mudstone with minor sandstone intercalation, unconformably overlain by Belite Formation and underlain by the Temburung Formation. The unconformable surface underlying Belite Formation represents a regional unconformity correlatable to DRU. Kudat Peninsula forms part of the northeastern limb of the northwest Sabah overthrust system. There are 4 geological terrains identified within the Kudat Peninsula, namely the northern Sabah terrain, which almost entirely consists of tajam member of the Kudat Formation, the Kudat Fault Zone, the Kudat Slump Formation, which comprise part of the Tajam and Sikwati members, and the Menggaris Duplex terrain that is part of the West Crocker Formation. There are a total of 7 outcrop stocks were observed throughout the study. Therefore, in this session, we will discuss one by one. The stock 1 is located in the southernmost corner in the Klias Peninsula, comprise a steeply dipping sand shale beds of deep water Temburung Formation. From the stratigraphic position of the fluid cast, it indicates the bed is yanging towards the southwest direction. The outcrop shows a typical turbidite succession with repetitive Buma sequence. It is characterized by predominantly shale and mudstone of TD and TE, division with sparse fine sandstone beds of TA. From the Buma succession, it suggests that the outcrop section represents distal part of turbiditic deposit. Besides that, Ophromorpha recta is associated with quite oxygenated environment, especially that is episodically interrupted by turbiditic flows, typically in bathyal and episode environment. Ophromorpha annulata was observed well preserved in the sandstone bed, which suggests a position within the lower batial to upper slope. Furthermore, the Ophiomorpha rudis is associated with high energy proximal and axial turbidite deposits. Stop 2 is located in the central part of Trias Peninsula, which consists of steeply dipping sand shale succession of deep water temburong formation. The outcrop is represented by more dominant sand beds of TA compared to the preceding Stop 1. Dominant TA compared to TE probably represent the position of proximal turbidite environment, followed by a shorter interval of mud suspension deposits. Ophiomorpha annulata occurs quite abundantly at this outcrop, which is associated with deposition in the lower batial to the upper slope environment. Stop 3 represents basal belite formation deposited unconformably overlying deep water temburong formation. These formations are separated by regional unconformity known as the DRU. Basal belite formation is composed of predominantly conglomerate with a few interbedded coarse grain sand deposited in fluvial environment. The conglomerates are composed of various grain size ranging from boulder to pebbles, which implies deposition in the high energy condition. The upper part of belite formation, whereas it consists of finding outward sandstone and shale succession, a fault was observed 2 meter displacement, which then infilled by shale in the later stage of deposition. Cross beddings were also observed within the sandstone, and burrows belong to Ophiomorpha nodosa was present, which could associated with the deposition in the marginal marine environments. Stop 4 represents West Crocker Formation. It consists of predominant thick beds of coarse grain turbidite sandstone. The outcrop shows a section that it has undergone intense tectonic deformation, resulting overturned bedding and folding. The presence of footcast at the base of the sandstone beds implies the bed has been tilted more than 90 degrees, indicating a younging towards the southeast direction. Ophiomorpha nodosa, which was associated with shallow marine setting, was also counted quite sparsely within the sandstone bed, suggesting intermittent shallow marine sediments transportation into the deep water setting. Stop 5 represents the Sequati member of Kudat Slum Formation, which occurs mainly within the central part of the Kudat Peninsula. Overall, this outcrop is dominated by highly steeping beds. It consists of deep water turbidite deposits with predominantly TA, TC, TD, and TE in the lower stratigraphic interval, and TA, TD, and TE in the upper section. Other than that, recumbent fur was also observed at the eastern side of the outcrop, which interpreted as a slum associated with thin sedimentary soft deformation. Stop 6 also represents Sequati member of the Kudat Slum Formation, which predominantly sandstone interbedded with shale. The Buma sequence observed at this outcrop is consistent with that in the Stop 5, which composed of TA, TC, TD, and TE at the lower stratigraphic interval, and TA, TD, and TE at the upper stratigraphic interval. Channel belts were observed consisting TC sandstone with common flame structure at the pinch out section of the channel. It shows that the section is younging toward the southwest direction. And lastly, Stop 7 is located at the northernmost tip of the northwest Borneo within the northern Sabah-terrain. It is dominated by the Kudat anticline and semi-concentric pattern of the rich valley morphology. The sedimentary section is represented by predominantly thick TA sandstone, overlain by TB and TC sandstone, and then capped by thin TE shale. Ophiomorpha nodosa was also observed within the sandstone bed with low abundance and smaller size. This stress fossil is associated with high energy environment, possibly within the proximal part of the turbidite succession. So there are 5 key discussion points identified from the study. However, we will discuss 2 of these points. Firstly, on the West Crocker Formation, it shows succession of thick bed coarse grain sandstone turbidite deposit as shown by TA, followed by thinner TB, TD, and TE. This observation indicates deposition took place under influence of high energy regime. Alternatively, it may suggest also deposition close to the sediment source area. In the West Crocker Formation, it has been intensively deformed, resulting in structural folding and overturned beds. This event is closely associated with compressional deformation in relation to subduction of dangerous ground towards the Borneo in the early Miocene. Another key discussion that we can touch here is the paleo environment of the northern Sabah terrain. The northern Sabah terrain exposed Stop 7 crop consisting of succession of thick TA sandstone beds, thin TC sandstone, and also TE shale. The observation suggests the turbidite event took place within the high energy deposition, which followed by decreasing energy as shown by TA-TC succession and ended by TE, bed mud suspension. It reflects the change of depositional regime from high to low energy, and this observation was also supported by presence of Ophiomorpha nodosa within the sandstone bed in low abundance and smaller size. These stress forces strengthen the fact that the outcrop is deposited within a high energy environment, possibly within the proximal part of the turbidite succession. So to conclude my presentation, sedimentary feature provide an indicative signature of stratigraphic position at the beddings, as well as the positional process involved at the outcrop. Stress forces also provide proxy for the position environment interpretation based on their burrowing behavior. Overall, the outcrop observation during the field trip allowed further sedimentological insights to be made and subsequently improve the sedimentological environment interpretation. So that's all from me. Thank you.
Thank you very much, Mr. Mukris Mubin, for these excellent presentations. So we now would like to invite questions from the audience. Dear delegates, please use the little green box at the bottom right to access the live Q&A chat box, and you can write your questions over there.
Hello, good afternoon.
All right, Mr. Mukris, there's no yet any questions from the floor. So let me ask you, from your point of view, what kind of the data that you can use to validate your findings on deep water turbidite sedimentary features that you found in the onshore Northwest Sabah?
Thank you, Mr. Shaz, for the answer. For the question, sorry. To validate our excursion on the outcrops, even though we only do our outcrop session for about a week, and we haven't get much what you call that time to go through in very detail for all those outcrop. So I would suggest we have to go back to the literature reviews and to confirm on our findings, or possibly we can extend our findings probably towards the seismic in the offshore nearby the area. That's what my opinion lah.
Okay, so thank you, Mr. Mukris Mubin.
Thank you.
So from the audience, there's still no questions from the floor. So I will proceed for the next questions from myself. Okay, so since you said that you didn't have chance to go for the fieldwork survey, right? So in the meantime, do you have any kind of data that can justify your findings, since you couldn't see from the real outcrop observations?
In my opinion, like I said just now, we can go back to the literature review, and maybe we can confirm back if possibly we have coarse information at the area. But I strongly suggest that to validate our finding, probably we can go back to our literature review and to see back whether our finding is corresponding correctly or not.
Okay, all right. Thank you, Mukris, for the answer. All right.
Thank you.
Thank you so much. Okay, we have to move to the next presenter, since we have very limited time now. So moving on, we now have the privilege of listening to Suzy Fikri Sahari from Basic Front Lab Asia on the comparison between conventional and high resolution measurements for unlocking the LRP potential reservoir case study. Please join me in welcoming Mr. Suzy Fikri Sahari to the podium.
Assalamualaikum warahmatullahi wabarakatuh, and a very pleasant evening to all of you. Ladies and gentlemen, my name is Sufi Zikri Sahari. I'm from basic from Lake Asia. And today I would like to present you a case study, a comparison between conventional and high resolution measurement for unlocking the thin laminated potential reservoir. So for today presentation outline, I will address the background of the low resistivity, low contrast or low resistivity pay interval, or formation in which what factor that we call them as LRAC or LRP interval, and also the objective of this study. And then we'll go into the study approach on how to resolve the objective of this problem, and also come to the result discussion. We'll show the final saturation curve, okay, and validation with the core data. And then we will go into the conclusion, and I also attach my references for this study, and then we can continue to our Q&A session. So, low resistivity, low contrast, or LRLC. Some also call them as low resistivity P or LRP. So basically, we know that this interval, basically, it will suppress the resistivity, measured resistivity value. And then when we compute our saturation from this low resistivity value, definitely it will give us high water saturation, and then we as interpreter will mistake it as a water bearing interval. In fact, this interval basically may have a hydrocarbon bearing interval. And according to Worthington, there are 6 causes for this phenomenon to occur, which are laminated shelly sand, fresh formation water, conductive mineral, fine grain sand, microporosity, and also superficial microporosity. So in his study, they have 6 factors, but for this study, we only focus only on laminated shelly sand model. So the objective of this paper, basically, like I said, we want to showcase the option in terms of approach on how to resolve for this challenge or problem, a kind of reservoir, this LRLC or LRP, laminated shelly sand reservoir interval. So if we don't have, here is the statement like, with the availability of advanced tool or higher resolution measuring tool, definitely it will become a determining factor for true water saturation computation, which will result in high water saturation, high accuracy water saturation output. But what if this advanced or high resolution measuring tool is unavailable, the data is not there? Okay, what choice that we have? So this paper basically want to answer that. If it's not available, what is the alternative left to unlock this challenging reservoir? Before that, here is the occurrence of shale and shelly sand elimination. We know that shale consists of more than 70% clay particles that normally deposited in the low energy environment, very calm, quiet environment. And this lamination, you can see from this is a cross lamination structure. You can see here, it's actually indicates cyclic surrounding energy that changes of the depositional area. And here you can see the example of parallel structure, and this is a lenticular structure. So the environment that normally associated with this kind of sediment structure configuration is like deep marine, lacustrine, mudflat, which is normally the environment that have a very calm energy. And we go to the next slide. Resolution of the tool. So in geology, point of view, in geology's point of view, the lamination thickness, they classify it as any sediment thickness that have less than 1 centimeter thickness sediment layer of sedimentation, then they call it lamination. But for petrophysics, a point of view, the thickness is defined based on the tool resolution. So basically, if the tool have a very high resolution, then it can resolve a very thin lamination of thin layer. Okay, so but if the tool don't have that resolution, so what will happen? Definitely it cannot resolve that thickness, and because of that, we cannot get a proper value. Here in this picture, you can see, for example, this is what we call as a resolvable. Means the tool can, the log respondent that come from the tool, it have almost 1-on-1, okay, compared to the true value. This is the mathematical model, but this is what they try to showcase here. If the tool have a very low vertical resolution, this is what going to happen. The true value, instead of it's supposed to be at this point, okay, the true value, but the measured log has been averaged, been suppressed. This is what happen to our conventional resistivity when we have a sediment thickness that below this tool resolution. It will tend to average the value, and because of that, the hydrocarbon bearing limited interval with low resistivity value and give us high calculated distortion, and that make us to miss this interval. And to resolve for this challenge, the concept of parallel and series resistivity has been introduced. So because of that, we have these three equations, and by resolving the true sand resistivity through inversion technique, we can manage to get our true water saturation, because we have true sand resistivity, and then we have true water saturation. So basically, sand shell lamination, it exhibits the anisotropy. So means you measure at a different direction, it will give you a different value. So here we have a horizontal direction and also vertical. Because of the configuration of sand shell lamination, it change the layer between the sand and shell. That's why when we measure it horizontally, the resistivity tend to be suppressed because of the current will take the least resistivity path. We know that clay component consists several metal elements like aluminium, ferrum here. Okay, and this conductive element that actually suppress this resistivity value. Supposedly, it gives a true resistivity that of sand interval that consists of hydrocarbon, which is high because of this element. It reduces the resistivity value. It's average because of this very thin sandwiches of the clay between the sand. So to solve that, we need to identify the true sand resistivity. So by doing the simultaneous equation inversion, so we can get this R sand, and then we will get that saturation, a true saturation for this kind of formation, sand shell elimination. And next is so this is our approach. Sorry, this is the what is this paper is about. Basically, we present two case study. The first is an inversion approach that using the advanced tool that measured the RV and RH, the vertical resistivity and also the horizontal resistivity, and then we use the module, module from the tech log to do the inversion to get the 2R sand, and then compute it using the Waterworks-Smith equation, and we compare it with water saturation from core measured using the Lean-Stark approach. And for the second case study B here, basically we're using the conventional measured resistivity tool And then we're using the Thomas table, famous Thomas table cross plot to do the inversion. Okay, and then again we compute using the Waxman-Smith, and we compare it with core saturation, which is using from Ginstock. And then we also run the conventional method that directly using the RD measured input log, and then we directly calculate the Waxman-Smith equation. So we want to highlight that this in the middle. Definitely, the conventional method is you can't resolve it using conventional method, but you need to use the inversion module with the option. If you don't have the advanced tool, you still can use conventional tool. Okay, and this is the result for the case study A. Here, this is how we select our endpoint. Basically, we're using this visual from neutron density and gamma ray to guide our endpoint selection. We try to reach as high as a regression coefficient as we could. And then basically here in the middle, it will give us the laminated shell volume. So when we manage to resolve the unknown for the laminated shell volume from this cross plot. Then after we get the volume, remember this is case study A. We have the advanced tool input. So we have the laminated shell volume, and then we have the unknown for the RP and RH come from the measured advanced tool. So from that we can resolve the true sun resistivity. And here is how we use our RP and RH. We're using the modified Klein plot, okay, in order to identify the optimum shell resistivity anisotropy for RV and also RH. This is our input log, RV and RH, and then we're using the cross plot to identify where is our shell point is. Here you can see this green interval indicate our shell point here, and this is the pay interval at this top part here, colored in the red coded interval, and so this is the red curve. Sorry, from the left side here we have a gamma ray log, and also here is a neutron density. This is a resistivity log. This is our porosity log, and this is our clay volume and also the net sand, which come from our inversion. The V clay is in the red dot color. It's come from core SRD, from SRD measurement. And here is our true resistivity sand in comparison with our deep resistivity. And here is our final saturation. We have 3 different curves, which is pink, blue, and also black. I will show in detail in the later slide. So, by the way, we're using this modified Klein plot in order to determine this shell point. You see, we can move this point, okay, to identify where is optimum. We don't just simply select our RP and RH at somewhere here, for example. Because of this cost plot, we know, okay, we should select it here. So that's how it guides us, and then we put it into our model. Here is the value for our RP and RH, and then it will be inversion and resolve for the true sensitivity. And this is for case study B, and this is where we only have the conventional tool RD data. We don't, for example, we don't have the advanced tool. So this is what we can do. And using the Thomas table plot, still we can resolve for the limited shell volume. But in this case, for the shell resistivity, we're using the RD, okay, instead of RB and RH. This model is able to model the saturation later. Here is the final result. Here you can see much more clear the composite layout here. Just don't get confused between case study A and case study B. With this core box A and core box B, it's not related. Okay, basically core box A, the sample taken from this formation. Core box B is taken from this formation. Is not related with the case study A or case study B. Just don't get confused. So here, if you can see, okay, let's focus on this track. It's indicate the saturation track count from the 3 different approach. Conventional approach that directly measured from the RD measurement, and the blue color is just now it's the pink color. The blue color is the inversion method using the Thomas fiber with the conventional RDIP log input. Okay, this is the blue color. You can see the result here. And then the black color is the inversion method using the LoRa module. And then we have an input of advanced tool for our RV and RH to resolve for our RV and RH during the inversion to identify our truth and resistivity. And the red dot is a core data. You can see how well it's matched between the this inversion saturation that come from the advanced tool. But I want to highlight that even though we don't have the advanced tool, but the blue curve here you see is still can be acceptable. I mean, better than nothing in comparison with the pink color. It's almost half. Here is like 80%, and the blue color is like 40%. It's almost half of the true value. And if you compute the volume using this pink curve, definitely we will miss this interval, for example, which contain a very significant 40%. What station is give you around what? 60% of oil saturation. Okay. And I think, yeah. So let's come into conclusion. Basically, in a conventional approach, definitely when we utilize directly our measured or conventional measured resistivity for our saturation calculation, definitely we will miss the reservoir, or if not, it will give us a wrong volume, wrong saturation. We will underestimate our oil saturation and overestimate our saturation. And inversion is a reasonable option to analyze the limited reservoir. Okay, in this case, even without having advanced resistivity measurement, RV and RH, we can still proven to yield a reasonable estimation of water, like I show you in the blue curve just now. However, the advanced resistivity tool RV and RH definitely will give a very high accuracy of water saturation, and just confirmed by the composite of this water saturation measurement just now in the black curve. I think that's all from my presentation. Thank you very much for the time. I think let's go to the Q&A session. Thank you.
Thank you very much, Mr. Suzy Fikri Sahari, for the excellent presentations. We are now open for the floor for the Q&A sessions. Dear delegates, please use the little green box at the bottom right to write your questions.
All right, thank you, Madam Shaz. I'm very sorry, first of all, I have a technical problem. I cannot open my camera. Anyway, we have one question here from
Yeah,
Dr.
let me read the question.
Okay, all right, no problem.
So we have a question from Mr. Khairul Arifin Mohamad Noor. Okay, from his questions, he says that there are 6 causes for LRSC, LRP to be occurred. How fine-grained sands, internal microporosity, and superficial microporosity can cause this LRLC, LRP phenomena?
All right. Thank you, Dr. Khairul. And I believe I presented in the first slide just now. Okay, basically this study is only focused on the first factor, which is a laminated sand shell lamination interval. But for those 3 causes to cause this phenomena, is basically because of it's related with high capillarity. Okay, as we know that very fine grains or superficial microporosity, all of these have a very fine pore throws of that stuff, which give rise to a high surface area. So basically, it's like it can appear as a shell effect. So in this case, it's more into low contrast. For example, like okay, shell is water bearing. It's have a bonded water. I means like because of that, it may give a how to say wrong interpretation. Instead of we identify it as hydrocarbon, it might be a water, for example, something like that. So it's more related into the high capillarity, which give the rise to a high surface area. Yeah, I think
All right.
that's all my answer. Thank you. Thank you.
Okay, thank you very much, Mr. Suzifikri Sahari, on the comprehensive answer. So I think we don't have any more questions from the floor. All right, so now we will move on to the next speaker. So ladies and gentlemen, our next speaker is Ms. Anur Samsudin from Basic Friend Lab Asia. She will be presenting on the significance of Ophiomorpha trace fossils as key sedimentological parameters for paleoenvironment assessment. Case example in Klias and Kudat Peninsula, Sabah. Please join me to welcome Ms. Anur Samsudin to the podium.
Assalamualaikum and hi ladies and gentlemen. Thank you for showing your interest and spending time to listen to this presentation. I'm Anur, a geoscientist from Basic Friend Lab Asia. I am representing my team to share our work entitled The Significance of Ophiomorpha trace fossils as key sedimentological parameters for paleoenvironment assessment, case example in Klias and also Kudat Peninsula, Sabah. So without further ado, I will proceed with the outline for today's presentation. I will start with the motivation in doing this work and also the objectives, and then continue with the study area where we did the work, generalized stratigraphy of onshore Sabah, the occurrence of the trace fossil, and then proceed with the discussion, conclusion, and then I will end this presentation with the acknowledgement and also the references that we had throughout this work. Generally, in Northwest Sabah, actually there are various geological studies where it ranges from tectonic and to stratigraphy. However, what it is still lacking in this study is on the ignofossil, where it is still lacking especially on the paleoenvironment assessment. So in this work, along with the sedimentological observation, we focus on these trace fossils identification and interpretation from the outcrops in order to improve paleoenvironment assessment in the area. So we had conducted the study in the Northwest Sabah around Klias and also in the Kudat, northern part of Sabah. So there are 4 outcrop locations in red dots as observed in these images. So we studied its sedimentological features and also ignofossil content. So in terms of the stratigraphy for this area, it is covered the stratigraphic interval of Temburong, Kudat and also Belait formation. So I would like to share the generalized stratigraphy onshore Sabah from Lim that covered Labuan, Klias, Crocker Range for Sapulut in the left, and then Kudat, Bangi, Sapulut in the right. So basically in general, Northwest Sabah, it is underlain predominantly by Oligocene to Upper Miocene West Crocker Temburong Kudat formation of deep water sediments in light blue color, and partly they have fluvial to shallow marine blight formation. Temburong and Kudat formation represent the younger formation of Rajang Group Crocker Foot Thrust Belt, and it is underlain the older formation is Crocker, Trusmadi and also Sapulut. So these 2 groups of rock are separated by late Eocene unconformities. So we proceed with the study area where we have 4 locations. This is location 1, location 2, location 3 and also location 4 with various rock types ranges from interbedded mudstone shale to thin and thick bedded sandstone of Belait, Temburong and Kudat formation. As for the location 1 and also location 2, we have Temburong formation of Oligocene to Upper Miocene, and it is composed of the interbedded sandstone and also shale. As for the location 3, we have Belait formation, Lower Paleocene, where it comprises the thick-bedded sandstone, glacial, clay with the conglomerate at the base. At the fault location, we have Kodat Formation with the Miocene age, exposed with the medium to thick bedded quartzose, feldspathic calcareous sandstone, and abundance of lignitic carbonaceous layers and glacial with the treated granites occurs in several places. So basically, to note that in our study, we identified there are 4 ichnotases of the trace fossil belonging to the genre of Ophiomorpha, and known as Ophiomorpha recta, Ophiomorpha rudis, Ophiomorpha annulata, and also Ophiomorpha nodosa. So most of them were observed in the well-preserved within the loose grain and also soft ground sandy substrate. We can see they have various orientation, like from vertical to incline, and then they have branches and unbranched. So the detailed description of the taxa can be referred as in the paper. So basically, to note that these trace fossil assemblages have been commonly used since a long time as one of the key sedimentological indicators to assess the paleo environment. So we have the stratigraphic record that left from the trace fossil, and it has been recognized as the close proxy to the depositional environment. So in our study, we focus on the Ophiomorpha ichnogenera, where it had like the strong association with the modern analogous dwelling burrows crustacean. And actually it is subject to control ichnotation, where found mainly in the fine to medium grain deposit. So basically, although it is very abundant in natural marine environments of ichnofacies of these Ophiomorpha ichnogenera, it is also known to be occurred in the deeper water settings. So in the deep water, Ophiomorpha usually reported particularly well oxygenated, and it had like medium to thick bedded tubular deposit. It could be related to the channel or proximal depositional loop fascies. So basically, I would like to show the Ophiomorpha nodosa in location 3 and also location 4 in this part and also in this part. So as discussed before, it is usually in the green and soft ground sandy substrate, where it might relate to the higher environment energy. So as for the Ophiomorpha, as here, we have in location 3 for the Polite formation here, and then here, which is location 4. Lower abundance of Ophiomorpha nodosa that were observed in the location 4 compared to the location 3, which probably pointing to the variation of the water energy. So when it comes to the other trace fossil like Ophiomorpha rudis, Ophiomorpha annulata, and also nodosa, and it is also well preserved in the analysis of the study area location 1 and also location 2. So what we would like to say, like here, it is strongly associated with the sandy substrate in the Temburong formation, and their occurrence varies from the high to very low abundance, where we have Ophiomorpha rudis ichnofacies that commonly occur in the very low abundance compared to Ophiomorpha annulata. And the relatively low abundance could be related to the sandstone facies association with the channels and also proximal lobe in the turbidite association. While for the Ophiomorpha rudis, we have some ichnofacies could be associated with the submarine fan environment. So to conclude, the trace fossil provide a close proxy for the understanding for the paleo environment condition, and hence it is a good key sedimentological parameters depositional in assessing the paleo dispositional environment. So in this study, we have Orudis, Ophthalmopharodis, Ophthalmopharodata, and also Ophthalmopharecta that could be associated with the deep water deposit, while Ophthalmophanodosa, which are related to the shallow marine deposit. So based off this interfacial association, the depositional environment are better assessed appropriately and improve the understanding of the environment, especially in the northwest area. So to finish up, I would like to acknowledge my company, which is Pacific Frontline Asia, and my team, and also Dr. Dalila for the constructive feedbacks. And then I'll proceed with the references that we had throughout the work. And then to end, I will open the floor for the Q&A session. So thank you for listening.
Thank you very much, Ms. Anur Samsudin. Ladies and gentlemen, unfortunately, we had technical problems to invite the presenter to the main stage. Therefore, I would like to proceed with the next presenter on the topic of lithology and fluid prediction using AVO methods inversions by Mr. Tar Nying from Basic Friend Lab Asia. Please welcome.
Good morning. My name is Tani Nimau. Today I am going to present my final year project on lithology and fluid prediction using AVO method and inversion. There are 8 outlines in my presentation, which starts with the problem statement, followed by objectives, scope of study, literature review, methodology, results and discussion, conclusion, and lastly, the recommendation. Conventional seismic and well log data can provide flawed information on subsurface structures due to misinterpretation of seismic and ambiguity of well log data. In reservoir characterization, not all indication and bright reflectors from well log and seismic represent direct hydrocarbon indicator or DHI. Structures such as coal layers and soft shale can also show similar indications on well log data and seismic section. Hence, it is vital to understand the quantitative measurements of the rock properties, which leads to the following fundamental questions. What do the bright spot indicators actually refer to? And will the elastic inversion study be useful in reservoir characterization to predict the lithology? The objectives of my project is to perform the AVO analysis and elastic inversion using elastic properties such as density, acoustic impedance, and shear impedance, and to characterize the reservoir by discriminating the subsurface lithology and porosity. The last objectives of my project is to propose the estimation of sweet spot location and indication of bright reflectors. The scope of study includes study well log analysis, depth to time conversion, and check shot data from well data, and to calibrate seismic to well type to generate synthetic seismogram, conduct acoustic impedance and elastic impedance calculations, generate AVO model and elastic inversion in interval software, to discriminate the reservoir characterization based on lithology and porosity, and to estimate sweet spots location. Then let's move on to the literature review. The study area of my project is an offshore oil field in Malay Basin. Malay Basin is located in east of Peninsular Malaysia, and it is 500 km long and 200 km wide. The geological context of the study area is characterized by a single reservoir target, and the provided data are as follows. The reservoir is located in Lower Eocene age, and it is a thin reservoir, about 70 meters, and there are very high proportion of limestone. There is also limestone reservoir included in an interbedded limestone shale environment. Lastly, there is a large and declined structure without any major faults present in the reservoir. The Malay Basin consists of two parts: southern northwest southeast trending structures and northern north trending structures. The figure on the left shows the stratigraphic framework and petroleum system of the Malay Basin, and the figures on the right show the cross-section of northern Malay Basin and cross-section of southern Malay Basin. AVO and inversion use elastic parameters such as compressional wave velocity, shear wave velocity, and density to produce acoustic impedance, shear impedance, and Poisson's ratio volumes. AVO techniques can be subdivided into seismic reflectivity and impedance methods. Seismic reflectivity methods include near and far stacks, intercept versus gradient analysis, and fluid factor. And the impedance methods include P and S impedance inversion, lambda mu rho or LMR, elastic impedance, which we use in this project, and the Poisson impedance. Elastic inversion utilizes AVO effects in pre-stack domain together with the use of VP, VS, and density informations. Shear waves provide information on the rock framework, while compressional waves interact with the pore field and rock matrix information. Pre-stack elastic inversion is defined by Archi-Richard equation as shown in here. And when pre-stack data do elastic inversion, it is crucial to make a better estimation by using the difference in VP and VS. The assessment is done by adopting an elastic approach, which is also known as elastic impedance, and the elastic impedance equation for small to moderate angle of incidence can be defined as follows. This is the methodology flowchart of my integrated study, which starts with literature review, followed by database, data preconditioning, seismic to well calibration, AVO modeling, pre-stack seismic inversion, discrimination analysis, then followed by reservoir characterization, and lastly, the estimation of direct hydrocarbon indicators. The methodology of my project after literature review is the database and data preconditioning. There are total 6 oil wells located within the study area, and they include gamma ray, density, sonic porosity, and water saturation logs. The data preconditioning process include preparing and exporting data from Easy Trace software to Interwell software, horizon processing, and normal move out and MO correction. Then for seismic to well calibration process, it is optimization of wavelet, which is a crucial procedure in seismic to well calibration. The process is broken down into multi-trace coherency analysis and multi-well, multi-angle wavelet estimation. There are 3 major steps in multi-well, multi-angle estimation, which is time shift determination, phase rotations determination, and energy normalization determination. The results are shown in the figure on the right side. After seismic to well calibration comes AVO modeling. In AVO modeling, we generate a priori model, which is an initial model which will be used as an input during inversion process. A priori model for elastic inversion includes P impedance, S impedance, and density initial models. After a priori model is generated, then it is followed by elastic inversion process. Elastic inversion generates optimized impedance models. It also maximizes the signal content and resolution while reducing the random noise. The quality of inversion results can be assessed by performing quality checks along with wells on maps and on seismic sections. When the elastic inversion process is done, the discrimination analysis process follows. The discrimination analysis aims to predict the lithology and fluid within the reservoir based on the inversion results. The discrimination analysis is a powerful technique which works in a probabilistic frame, then followed by the reservoir characterization. The elastic parameter computation module is generated to compute key elastic parameters such as Poisson ratio, VP-Vs ratio, intercept gradient attributes, lambda rho, and mu rho attributes. Reservoir characterization is conducted by applying porosity trend on the reservoir lithology after being post-processed. Then let's move on to results and discussion. The first step in results and discussion is the AVO analysis. In AVO analysis, AVO model is obtained by inserting the P impedance, S impedance, and density log values between well locations and along the correlation lines through spatial interpolation method. Afterward, the model is used as a starting point of the inversion iterative process. The figures on the right shows the acoustic impedance log showing time shift in well 1 and the report summary of wavelet estimation. Then the results of elastic inversion analysis shows the inline and cross-line correlation length, which is linked with the lateral continuity of the impedance distribution. The comparison between the a priori and inverted impedance trace at calibrated well locations on the figure on the right shows that the inversion results represents the impedance variability at well location. The results of reservoir characterization is to assess the phases discrimination by conducting several tests such as a direct assignment and cross validation. In this figure, the yellow lithology between the two horizons correspond to the reservoir, while the blue lithology corresponds to limestone and green to shale, respectively. The reservoir is also enclosed by limestone and shale layers. The results for estimating of DHI, direct hydrocarbon indicator, is the porosity trend. The porosity trend for the whole seismic is obtained by using an analysis of well data. Then a derivation of formula is used as a parameter to generate crossplot between P impedance and porosity only on the reservoir level. Then a trend curve is computed to define a linear relationship. In the figure, we can observe that a thick portion of reservoir lithology is observed on the left side within the reservoir interval. Well, the conclusion, the integrated study between AVO analysis and elastic inversion using well log and seismic data enables to evaluate the reservoir characterization, especially in reservoir lithology. The optimal model from the elastic study assists in classifying the reservoir parameters such as porosity. The elastic properties generated from the study are useful in discriminating hydrocarbon-bearing formations filled with gas from non-gas bearing formations and estimating bright spot location as well as reservoir delineation. And hence, these advantages fill up the pitfalls of the conventional ways and provide more specific information on predicting the reservoir characteristics. For recommendation, the reservoir characterization and delineation study can be improved by determining the other petrophysical properties such as permeability and water saturation. Interval and Easy Trace software are very convenient and reliable for seismic inversion studies. Interval is an advanced seismic inversion software dedicated for post-stack and pre-stack elastic inversion in both 3D and 4D seismic data. Easy Trace is a well-log analysis and processing software which features a multidisciplinary 1D data processing and editing tool for early stages of the study such as database and data preconditioning process. The interaction between the two software is also very smooth, making it easier to conduct geophysical studies. These are the reference I use for my project, and this is all for my presentation. Thank you.
Thank you very much, Mr. Tang Yingying. Unfortunately, we don't have any Q&A sessions as we don't have the presenter today. Ladies and gentlemen, we have come to the end of these technical sessions. On behalf of Icer, I would like to apologize for the unavoidable technical problems that we had earlier. And I would like to thank each and every one of you for your participations and patience throughout the sessions. To end the sessions, we now have the privilege of watching to a video provided by our co-organizer, Basic Front Lab Asia. Please join me in watching the video presentations at the podium.